So we finished our discussion of valence bond theory, and now we're going to turn our attention to the other bonding theory, which is molecular orbital theory. So why have two theories? Well, it turns out that each theory has its own strengths that we can use in particular contexts where the other one might fall short or not explain things as thoroughly. If I had to pick one or the other, I'd probably go with molecular orbital theory. As a bonding theory, it's going to give us a little more bang for the buck, if you will. It also gives us a lot of information about what's going on in reactions. But be that as it may, let's start in by figuring out what are molecular orbitals, and then we'll go from there. So atomic orbitals, which is what we've been working with so far in this packet, are wave functions. And so what we've been doing with them is combining them in various ways mathematically. Okay, we kind of glossed over that part of it, but in making hybrid orbitals, that's what we're doing, is combining these atomic orbital wave functions in using various mathematical processes. An atomic orbital is localized on a particular atom. So atomic orbitals belong, if you will, to particular atoms, as opposed to molecular orbitals. Molecular orbitals are spread across two or more atoms. Now, the way that we get molecular orbitals is to start with atomic orbitals. Okay, just like the way that we got hybrid orbitals was to start with unhybridized orbitals. So our basis set for making molecular orbitals is just going to be whatever atomic orbitals we're using. The atomic orbitals that we use can be hybridized or unhybridized. And the process of combining them or mixing them mathematically to form molecular orbitals follows the same guideline that we saw with the hybrid orbitals. If we want 3 hybrid orbitals, we needed 3 orbitals from the basis set. If we wanted 4 hybrid orbitals, we needed to use 4 orbitals from the basis set. So however many molecular orbitals we make, that's how many atomic orbitals we had to put into the process to make them. So the number of atomic orbitals that we put into the mathematical process is equal to the number of molecular orbitals we get out. So we're going to look into how we construct these orbitals. It's done by what's called a linear combination of atomic orbitals, or LCAO. That's just the acronym for the math that we're doing to get to the molecular orbitals. So atomic orbitals, like all orbitals, are waves. And if we think back to physics, if you've taken physics, you can combine waves largely in 2 ways. In constructive interference, what you're doing is creating an in-phase combination of waves. So we're going to draw some cartoons for this that are kind of oversimplifications, but should serve to get the point across. Okay, so let's say that you have these 2 waves. So if you combine them in phase, what's happening is that you're lining up the positive region of one wave with the positive region of another, and the negative region of the first wave with the negative region of the second. So as you mix these waves, what's happening is that you'll end up with an increased amplitude of the wave. So it reinforces the wave. By contrast, you have what's called a destructive interference, which refers to an out-of-phase combination. So let's look at another set of cartoons. Of a pair of waves. So let's say that we take the wave on the right and we place it on top of the wave on the left. But we do so in a way that the negative phase of the right-hand wave is going to align with the positive phase of the left-hand wave, thus canceling it. And so you're going to get a diminution of the wave, or a destruction of the wave. So if you have a pair of atomic orbitals, which again are wave functions, you can combine them in two ways. So you can combine two AOs, atomic orbitals, either in phase or out of phase. So those are the two possibilities and the only two possibilities. Now let's think about the results when we do these combinations. When we combine two atomic orbitals in phase, the result that we get is a molecular orbital that's going to be lower in energy than either one of the atomic orbitals that we combined. So when we combine two atomic orbitals in phase, the result we get is a molecular orbital, we'll say MO for molecular orbital, that is lower in energy than the atomic orbitals we combined. By contrast, when we combine two atomic orbitals out of phase, what we get is a molecular orbital that's higher in energy than either of those atomic orbitals. So the corollary to our first statement, when we combine two atomic orbitals out of phase, then what we get is a molecular orbital that is higher in energy than either of the atomic orbitals. And remember, the number of atomic orbitals that we put into the mixing process is equal to the number of molecular orbitals we get out. So we're going to get an in-phase combination and an out-of-phase combination. Okay, so how does this play into bonding? Let's look at a molecular orbital diagram, which is basically a picture of how the bonding is constructed in a particular molecule for H2. Now, the starting point for molecular orbital theory is valence bond theory. So you have to know what orbitals you would have invoked in valence bond theory to know which orbitals you need to combine to make molecular orbitals, to explain the bonding in that way. So let's think first about what we drew for hydrogen in terms of the valence bond model. So what we had was a pair of s orbitals, each with an electron. With a region of overlap between the two hydrogen nuclei. And so each of these is a 1s orbital. Each of these is bringing one electron to that bond. So a molecular orbital diagram shows the atomic orbitals that you're combining in and out of phase, and it shows the resulting molecular orbitals. So we're going to construct the diagram using the template that I've provided on the page. So first of all, let's think about what we're doing here. So we have two atomic orbitals. So we're going to make two molecular orbitals by virtue of the in-phase and out-of-phase combinations that are available to a pair of orbitals. Now, in a molecular orbital diagram, the atomic orbitals are on the sides of the diagram. So let's start drawing those things in. So over here on the left part of the diagram, I'm going to say that this is a hydrogen 1s orbital. So that's the 1s orbital on one of the hydrogen atoms. And then over here on the right is the other hydrogen atom's 1s orbital. And each of those contains one electron. Now the remaining orbitals, the remaining lines in this diagram, are the molecular orbitals. So the molecular orbitals appear in the middle of the diagram. Okay, and then finally, what we're going to see is that the electrons in the diagram appear twice. They're going to show up in two places. So we include them in the atomic orbitals that we're going to combine to create our new molecular orbitals, but we also show them in the molecular orbitals that are the results of that combination. So the electrons appear once in the atomic orbitals and again in the molecular orbitals. Okay, so let's do this. So the first thing let's work on is the in-phase combination. So we're going to combine the two hydrogen 1s orbitals using a mathematical process in an in-phase fashion, which is going to give us a molecular orbital that's lower in energy than either of these two. That's the line at the very bottom of the diagram. Now typically what people will do is draw a little dashed line connecting the atomic orbitals to that molecular orbital so you can see what the origin of the molecular orbital was. So this is our in-phase combination. And because it's a lower energy orbital than the atomic orbitals we started with, it's called a bonding orbital. So we can add that in down below. A bonding orbital is a molecular orbital that is lower in energy than its contributing atomic orbitals. Contributing atomic orbitals meaning the atomic orbitals you use to create it. Okay, so that's our in-phase combination. We'll look at a picture of the orbital in just a second, but now let's do the out-of-phase combination. So that would be the line at the top. So again, we typically draw dashed lines to connect the molecular orbital to the atomic orbitals we use to create it. So up at the top here is our out-of-phase combination. And because this is a higher energy orbital than either of the contributing atomic orbitals, this is an antibonding orbital. So let's add that in down below, that an antibonding orbital is a molecular orbital that is higher in energy than its contributing atomic orbitals. Okay, now we're going to look at pictures of the orbitals. So let's take a look. So over here on the side, I'm going to draw a pair of nuclei. And here is an orbital, like so. That dashed line that I drew initially is the bond axis. And these dots are nuclei. Okay, so this is the orbital that results from the in-phase combination of those two 1s orbitals. Okay, notice that it's all in one phase. Now, I'd like you to imagine something. Imagine that this is a watermelon, because that's more or less the shape of this orbital. So imagine that you have this watermelon, and then imagine that it's impaled on a yardstick. Okay, so the bond axis, pretend that's the yardstick, and then you've got a watermelon on it. And so holding the yardstick on either end, you can twirl it with your hands, okay, so that the watermelon starts to rotate. So you're rotating here. And so if you were to, at any point in that rotation, look away and then look back, it would appear that nothing has changed. And so you could do that numerous times, but the orbital is always going to look the same as you rotate it around the bond axis. That's an example of what we call cylindrical symmetry. So this orbital is cylindrically symmetric, which means that we call it a sigma orbital. So not only is this a bonding orbital, it's a sigma orbital. Okay, so now let's take a look up above at a picture of the antibonding orbital. So I'm going to start with the bond axis again. And then draw these two shapes. And then for one of them, we're going to shade it. Okay, so the antibonding orbital has two lobes. Notice that they're in different phases. So anytime you have two lobes in an orbital next to each other, they're always going to be in different phases. Always, always the case. And remember, when you go from one phase to another, you pass through a node. So there's a nodal plane that's perpendicular to the bond axis and perpendicular to the page. These are two spheres. They're in different phases. So now imagine that you have the same yardstick, you've eaten the watermelon, and now you've impaled a pair of oranges on the yardstick, much like the picture shown up above. If you start twirling the yardstick, it's never going to look different. Okay, so you can close your eyes and then open them, or look away and then look back. But as you keep twirling, the appearance of the orbital is never going to change. So it too, like the bonding orbital, is cylindrically symmetrical. However, to distinguish it from the bonding orbital, we call this one sigma star. So this is the sigma star orbital. Notice the presence of this nodal plane, and then let me highlight the nuclei. So you have a nodal plane, which again, just to remind you, represents an area where there is a 0 probability of finding an electron. Okay, so that has a consequence for how we think about things, but speaking of electrons, we haven't finished our diagram yet. So we brought two 1s orbitals together. We combined them in phase and out of phase. We've labeled everything. We have the bonding, the sigma bonding orbital, and the sigma star antibonding orbital. And now all we need to do to finish the task is to take the electrons that came in with the hydrogen atoms and put them in their new home. Okay, now, the molecular orbitals are the ones in the middle of the diagram. So your new set of orbitals that you want to fill up with electrons, or put electrons into, would be the bonding and the antibonding. So we would use the same rules to put electrons into those orbitals as we did when we put electrons into the diagram for carbon, which is to say, Aufbau, Hund's rule, and the Pauli exclusion principle, which means that we're going to start by putting an electron in the lowest energy slot, and the next one, because we have two, is going to be paired in the same orbital, paired with the original electron. Okay, so remember, over there on the left where it says electrons appear twice, once in the atomic orbitals, and then again in the molecular orbitals that we've created. Okay, now let's do a thought experiment. Let's map out a quantity of energy. So let's say that this is some quantity of energy, we'll just call it delta E. And let's say that you can take one or both of those electrons that are in the bonding orbital put in delta E worth of energy and promote either one or both of those electrons up to the antibonding orbital. Well, the antibonding orbital, like all antibonding orbitals, shows a node between the nuclei. So, how stable is it, if you're looking for bonding to occur, to try to have electrons in an area where there's a zero probability of finding electrons? What do you think that means in terms of bonding if an antibonding orbital is occupied? Now, if you said that that would cause the bond to break, you'd be absolutely correct. So what we're going to say, as a general rule of thumb, is that populating, which means putting electrons into an antibonding orbital, destabilizes the corresponding bond. And for what we'll see, that means that the bond will break. So if you put electrons into an antibonding orbital that's associated with a particular bond, that bond is going to break. Okay, so the last thing we have to do on this page is fill in a definition for a non-bonding orbital. Now, we didn't have any of those in this diagram, but we'll see some of those later on, and they'll pop up all over the place, so we need to know what they are. A non-bonding orbital we can think of as a molecular orbital that has the same energy as an atomic orbital. Okay, let's practice this approach a few more times. So we're going to do a couple more diagrams. One is for an ion, H2+. Okay, now that plus tells you that you're short one valence electron. So you're still bringing together two hydrogen atoms, but in the case of H2, each one of them had an electron. In the case of H2+, you only have one electron. You can put it in either one of those hydrogen 1s orbitals. Just like we saw for H2, the 1s orbitals are going to combine in phase. That's going to give us a sigma orbital, which is bonding. And out of phase. And that gives us a sigma star orbital, which is antibonding. The electron that came in with one of the hydrogen atoms now finds a new home in the lowest energy slot we can find for it, which is the sigma orbital. Okay, let's repeat the exercise for dihelium. Now, helium is also using a 1s orbital to contain its two valence electrons. So each of the helium atoms in this exercise has two valence electrons. But we're doing the same thing that we've done for the past two examples. We're making an in-phase combination and an out-of-phase combination. And what that's going to do is generate a sigma orbital, which is bonding. So we would call that a bonding molecular orbital, and a sigma star, which is an antibonding molecular orbital. The two helium atoms brought in a total of 4 electrons, so we need to put them into the new molecular orbitals. And again, those are going to be the orbitals in the middle of the diagram. So the first one goes in the lowest slot, then we pair the second one with it, and then the next place to put 2 electrons is going to be up in the antibonding orbital. Now, one of the things that molecular orbital theory can provide us is an understanding of what's called the bond order. So the bond order is a simple calculation that we can do, and it goes as follows. We take electrons in bonding orbitals, and subtract electrons in antibonding orbitals, and we divide that by 2. Okay, so for a particular bond, we're going to take the electrons that are in bonding orbitals associated with that bond, subtract off any electrons that are in antibonding orbitals related to that bond, divide the result by 2. All right, so let's do this calculation for the 3 molecular orbital diagrams that we've just completed. So for hydrogen from the previous page, we had 2 electrons in bonding orbitals, we had no electrons in antibonding orbitals, and we divide that by 2. The result is 1. So we would say the bond order for H2 is 1, and a bond order of 1 corresponds to a single bond. Okay, let's repeat the calculation for H2+. We had, for H2+ up above, 1 electron in bonding orbitals, 0 electrons in antibonding orbitals, and when we divide that by 2, the result is 1/2. Okay, now, ideally, to make a bond between 2 nuclei, you'd like to have a pair of electrons. Okay, since you only have one that's holding those, or trying to hold those 2 nuclei together, it can do it, but it might not last very long, and it's going to be a pretty weak bond compared to a regular single bond. So here what we would say, the bond exists, but is weak. And it may be short-lived. Okay, and then finally for dihelium. 2 electrons in bonding orbitals, and there's 2 electrons in the antibonding orbital, and when we divide that by 2, the result is 0. A bond order of 0 is telling us that bond cannot exist. So the destabilization of having electrons in a higher energy antibonding orbital offsets the stabilization that you get by having electrons in a bonding orbital. Now this relates to a diagram that you may have seen. It looks something like this. So energy, here's positive, here's negative, here's the 0 point. And so at some point in general chemistry, you probably saw this diagram. This is called a Lennard-Jones plot. And what it's showing us is something about bonding. So way over here at the right are the 2 nuclei that are going to participate in the bond, but they're completely separated from one another. Okay? On our x-axis, what we're doing is measuring the distance between the nuclei. So as you go from left to right, that distance becomes greater and greater. As you start bringing the nuclei closer and closer to one another, you're moving left on the diagram along that blue line. And at some point, you're going to get to this low energy point that I've just denoted here, and now I'm highlighting. This distance right here is going to be the average bond length for whatever type of bond we're talking about that exists between those 2 nuclei. So that's the sweet spot. Now once you start pushing those 2 nuclei closer and closer together, And again, now you'd be moving this way on the curve. The energy starts to shoot up because the repulsions between the two nuclei and the electrons associated with them overwhelm the attractive forces that you get when you're at the bond. So the bottom line here, the moral of the story, is that electrons in bonds are more stable, that is to say, lower in energy, than electrons that are not in bonds. So more stable means lower in energy. So we'll come back to that idea in a little bit.